right, and so the first thing we want to talk about is just the general thing that each of the numbers did in the equation that you guys figured out. So you guys answered all these questions in that investigation, and hopefully right now as a group we're clarifying and summarizing, right? So first of all, how could you tell if the graph would open upward or downward? So these graphs were shaped like V's. How could we tell? Up versus down. What can we look at in the equation and be like, I know which way that faces? Good. So if A is positive, okay, which means greater than 0, then the graph is going to open upward, versus if A is negative, the graph is going to open downward. So A actually serves multiple functions, right? One part of it, the sign, the positive, negative, is telling me up or down. However, the number value of A also changes the graph. So you guys had that page where you got to just slide the A value back and forth and see what happens to the graph, right? So can anyone tell me, we now know up and down is determined by if A is positive or negative, but then what else did the A value do to the graph? What other effect did it have? Yeah. Good. It also changed the slopes of the lines, okay? So here in the directions, it said things like translations, stretches, compressions. We're going to get more into that in between the first and second unit. So right now, what I would expect you to do is to be able to identify that A changes the slopes. Okay. And what effect does that have on the V that you're looking at visually? Yes. Good. Okay. So it kind of went like if, I'm going to write this a little bit pretty mathematically notated, but the absolute value of A, right? If it was like bigger than 1, like Graham is saying, so if it was 3, 4, 5, stuff like that, 10.2, I don't know. You saw it get closer together and more narrow, right? Because the slope, you guys are saying it controls the slope. So when it's bigger than 1, the slope got steeper than the original one that we looked at, like the parent, right? So when A was greater than 1, absolute value, because I don't care about the positive, negative, that's a different thing for me, right? So if the number part was bigger than 1, okay, then I saw it get narrower. Okay? Or have those steeper lines, okay? Compared to if the A value was less than 1, so if you guys went over to like 0.6, okay, 0.2, negative 0.2, compared to that original one, that meant it got wider. And the original one was just the original graph you saw that we said was called the parent function. Did you guys see that language in there? Okay, that just had like 1 for A, 0 for H, 0 for K, like the most basic absolute value function, just the absolute value of X. It has slopes of 1. So if the A value gets larger than that, you see the narrow. If the A value gets smaller than that, you see it get wider, okay? And like I said, at the end of Unit 1, we'll talk about whether those are called stretches and compressions and things like that, and we'll use more rich mathematical language. Right now, I just want you to identify, like, this number does this to the graph, okay? All right, what about how H changed the graph? So the H was here in our formula. How did that affect our graph? Yes? Okay, close. You have K, so we'll write down for K first. Yes? Good, good. So the H was the one that was moving horizontally left and right, right? And notice that the H is in here affecting the X value, right? Like H is a number that you're subtracting from the X value, so it makes sense that H is going to affect the X value. Like before the absolute value is even done, it's changing the location of the point further left or further right because I'm adding or subtracting something to where the X used to be. Is that okay with everybody? All right, so H is going to translate our graph, if you remember that from geometry, or shift, okay? Left or right. Okay? And if H is less than 0, if H is negative, it's moving to the left, and if H is positive, it's moving to the right. But remember, H being negative or positive doesn't mean your equation necessarily has a plus or a minus, right? We have to let our brain kind of wade through. The equation says this, that means H is actually worth this, okay? And then what does K do? Yes? Perfect. Yeah, it changes it vertically because look where k is being added. K is being added after you're finished with the absolute value, right? So it's like you already took the absolute value and like plotted that point like, oh, when I plug in -1, the absolute value is +1. But now I want to add 5 to it. Okay? So it doesn't move it left or right, it moves it up or down. Okay? Because it's being added after you're done with the main function that you're trying to use here. Okay? So the k value is going to shift up or down. And again, the correct terminology for that is translation, but we're going to do the correct terminology after we're finished with this unit. And so when k is positive, it goes up, and when k is negative, it goes down. And k is a lot easier to immediately see the value because the equation has a plus. So if it says -3, you know k was -3, okay? It's less kind of thinking than we have to do for h. Is everybody okay with the values of each of these things and how they affect the graph after what you saw yesterday in your investigation? Yep. Okay, when I move the screen, it's going to change this. Does anybody need anything else on here? Okay. All right, so let's just look at an example. So when you guys go to graph them, hopefully you guys put some different things on Desmos, but kind of the relationship, if you were graphing this problem right here, okay, you would immediately want to pick out the h and the k value because those kind of give you that vertex of your absolute value function, okay? And then the a value gives you the slope, so you know you want to use 3 as the slope, so rise 3, run 1, and you want the v to be up. So you would plot this point first, and then you'd go up 3 over 1, and you'd kind of mirror that on the other side as well. You could go up 3 over 1 again, and you'd mirror that on the other side as well. And then you'd have your absolute value graph. Okay? And if you were writing the equation, you'd do the same thing. You'd look at the graph and find the vertex, and you'd identify your h and your k, and you'd count the slopes from the lines, and you'd be able to get your a, and you would make a positive or negative depending on if it faced up or down. Is that okay with everybody, that relationship? Okay. So we're actually going to fill out a different paper to practice graphing an absolute value function. So you guys made those little like portfolio Google Drive things, right? Okay. So in there, we said we're going to have you put your notes, your quizzes once they're corrected, and something that we said we called the Cartesian catalog. Kind of sounds like a silly name. Okay. The Cartesian catalog is basically, you're going to get these same papers every time we graph a new function. So it's basically like a mini textbook just about how each function works. And so for each function, we're going to parent function like you guys saw for absolute value. And parent means the most simple one. We're going to do it for quadratics, cubics, logs, exponentials, all of them, okay? And then we'll always do 1 or 2 examples with it as well. And so you'll just have like a whole section of these that remind you the shape of each different function we've studied and give you an example of them and have these things listed called the characteristics. So the characteristics of the graph you're going to see over and over again in each different thing that we graph. So not only do we want you to know what the parent shape is and its behavior, we want you to be able to graph a new one, and we want you to be able to identify all these things on the graph. And you're going to see the same list of things with every different type of function that we graph. Okay, so our graphing is going to seem like we're doing the same thing over and over again with each new shape that we learn. Is that okay with everybody? So you can keep these with your absolute value notes if that's the way you'd like it organized, or you can have like kind of a separate section where you keep just all the different graphs that we've learned if you like. Okay, you'll get these papers throughout that time. Okay, so I'm going to open one up and we're going to go through one. Why don't you guys, while I'm opening it up, if you guys can graph the parent function, if you remember it from yesterday and where its vertex would be, and see if you know any of these qualities of it here. Or if you're just comfortable with graphing but not the characteristics, see if you can graph the parent and the other one that's listed here. Okay? Yes, Graham? There are. So normally it's the top drawer here. All these supplies you guys are welcome to get, but it's out because my other class is doing a lot of measuring right now. So straight edges are there if you need them. All right, I had you guys get started, but I found it quickly. My graph's too big. No, okay. All right, so parent function, what did it look like? What are you guys putting on your graph right now? Where was the vertex of the parent function? Yes. At the origin. Good. 0, 0. Okay, when I plug in 0, I get 0. So parent function, vertex at the origin. Okay. What are the slopes of the lines in the parent function? 1, right? When we said, how does A change? We said, when the absolute value of A is bigger than 1, this happens. When it's smaller than 1, this happens. And we said things like wider and narrower. We were comparing them to this original parent function. We always compare to the most basic form of the graph, which is the parent function. So if we use a slope of 1, we get something like this. If I can draw straight lines, which I'm clearly not very good at. So are we okay with what that looks like? Okay. And then how would the graph be different if we were forming the other graph? Where did you guys put your starting point? Did anybody get a starting point, or do they look at this and they know where the starting point should be? The vertex point is kind of where I'm talking about starting. Yes. Good. 2, 6. Is everybody okay with how she picked out h and k? H is a value of positive 2. K is a value of positive 6. X is going to be a Will the V face upward or downward? Downward. How do you guys know? The negative A value, right? Okay, and so then I know that I need to draw 2 lines. They both should be going downward, but in the opposite directions. And what should their slope be? Negative 2 over 3. So basically, the rise should be 2 and the run should be 3, but I should make sure they're going downward. So I'll go down 2 and to the right 3. Then I'll also mirror that on the other side like I went down in order to make the V face downward with that reflective property. I'm going to draw a couple more just because I can't draw straight lines well up here. Is this okay? I'm going to write the equation over here for me to save for later. My screen, in order for you guys to be, for it to be big enough for you guys to see, but then also get everything up here written, causes me to scroll a lot, which means I'm going to lose my cute little graphs here. So is everybody okay with our graphs? Does everybody have on their paper the graphs? Because you're going to want to look at them when we're going through the characteristics. Am I going to scroll and be gone? Yeah? Okay. So I can't write that high. So we'll do the first half of the chart for each one side by side. So we'll just kind of practice each thing twice. And then we'll do like the bottom half of the chart. Okay? So let's start with the parent function and go first through these first 5. Vertex, x-intercept, y-intercept, domain, range. Okay? So what's the vertex of the parent function? You guys stop me if you have any questions, okay? We're kind of just discussing it and putting it up there, but if something doesn't sit right, you completely have the right to ask a question. What is the x-intercept of the graph? Yes. Good. It hits the x-axis at the value of 0. So in an x-intercept, here's what we know. The y-coordinate is always 0 because it's on the x-axis, and then we figure out the x-coordinate, which in this case, we happen to be able to see it really nicely on the graph and could just pick it out as 0. Okay. For the y-intercept, we know the x-coordinate is always 0, and then we try to look for where the graph crosses the y-axis. What's the y-intercept of this graph? 0. Okay. So it's 0, 0. And we write those as points. Okay. What is the domain for the absolute value function? Yes. Good. So it's all real numbers. You can plug in any x, and you'll get some point that corresponds somewhere on your V. So for domain and range, you guys can write them either way. So I'm okay if you wrote this or this. I will make you write intervals wherever it says interval. So we'll talk about that in a minute. Okay, so all reals, or you could write it as negative infinity to infinity. What was the range of your parent absolute value function? So what y values does that function contain? Yes. Yeah, I see that. It has a minimum at 0, but it has everything above 0. So all y values greater than or equal to 0. Or if we write that in interval notation, that would be from 0 to infinity. Okay, and the square bracket, because 0 is included. We actually hit a y value of 0. So let's do the same things for our graph that's slightly more complicated because it has an a, h, and k value. All right. What was the vertex for the second graph that we graphed? Yes. 2, 6. Excuse me. Okay. So x-intercept and y-intercept. So can you see the x-intercepts clearly on the graph? Are you positive where it crosses through? Yes? Okay, does it hit at one point? What if we weren't positive where it crossed through? How do we find an x-intercept if it's not clearly crossing at like 5 or something? Yeah, Graham. Good. Okay, we can plug into the function a value of y and solve for x. Specifically, what value of y do we know exists for the x-intercept? 0. So I have a value of 0. So I plug 0 in. I'm going to do the work right here to my equation. And I solve this equation. So solving this equation first involves isolating the absolute value. It's a lot easier when we get to plug in for x, right? Because y is already by itself, but this is a little bit more difficult. So I get negative 6 equals negative 2/3 times x minus 2. And then I want to get rid of this negative 2/3 here. So I'm going to multiply both sides by the reciprocal of that. Still negative because I want to make it positive. So 3/2. Because when I multiply by 3/2, this and this will cancel out to just be 1. So I'll have x minus 2 equals whatever I get here, which happens to be 9. Oh, sorry. I'm trying to get my bit of... I get the absolute value of x minus 2 equals 9. But remember what absolute value means. What number could be inside these absolute value bars, and when you take the absolute value, you end up getting 9. So I'm not asking for x yet. I'm just saying what number can you take the absolute value of and you get 9? 9 or negative 9. So that's where we're getting, see how your v is crossing the x-axis twice? It has two x-intercepts because the number inside of the absolute values could exactly equal 9, or it could actually equal negative 9, but when I take the absolute value, it's turning into that 9. Okay, so when there's absolute value bars here, it's really two ideas that you need to consider and finish solving for. Okay, so we should get that x could equal 11 or x could equal negative 7. Okay, we have two x-intercepts, 11 as well as negative 7. Okay, is this all right? Is there a possibility you would ever have more than two x-intercepts in an absolute value function? No. Is there a way to only have one x-intercept? How would you just have one x-intercept? Yeah. Good. The vertex would have to be on the x-axis. Is there a way to have no x-intercepts? Yeah. And when would that happen? Good. Yeah, move that k, right? Like if you're down, move k down so it doesn't hit it. If you're up, move k up and then you don't hit it, right? So we have to be really careful with our solving and kind of use our graph to help us as well to be aware of the fact there could be none, there could be one, there could be two. A lot like quadratics, okay? It has a lot of similar behaviors just because not u, but v are not that far off as far as shape goes, okay? Yes. You write them both. Uh-huh. All right, y-intercept's a bit easier, right? We just get to plug in 0 for x, so a little bit less work. So for the y-intercept, when I plug in 0 for x, I'm going to have y equals negative 2/3 absolute value of 0 minus 2, and then plus 6. So 0 minus 2 is negative 2, but the absolute value of that is positive 2. So this is really negative 2/3 times a positive 2 plus 6. Oh, hi. Just so okay. So this is negative 4/3 plus 6. 6 is like 18/3. And so that gives us 14/3. Okay. So my y-intercept is that. See if that makes sense on your graph. Like what is 14/3? 3 goes into 14 4 times with 2 left over. So like 4 2/3. Does your graph seem to cross at a 4 2/3-ish kind of spot? Yeah, okay? So all that information should always kind of correspond. All right, what about the domain? All real numbers, okay? All the absolute value functions are all real numbers. You can plug in anything, add, subtract stuff to it, and then take its absolute value, and you're still going to get an answer. Things like square roots are where we're going to have issues with saying all real numbers, because if you try to take the square root of a negative, you're kind of stuck, right? As far as the real numbers go. So things like this, where you can always calculate them, you get your domain of all reals. What about the range of this function? Someone new that hasn't talked to us yet. What do we think is the range? Yes? Okay, so she says y is less than 6, yes? Okay, should we include the equal to also? Do we hit the 6? Yeah, okay. So she identified the maximum value. Okay. And that the graph goes below that the entire time. So in interval number, okay. Any questions on intercepts, domain and range, or vertex? We're okay? All right. So I'm going to scroll it up. Does everybody have what they need from there? Right? And then we're going to talk about this. I might save increasing and decreasing interval for last. They don't require a lot of work, but they require thought, okay? So we'll see. Not that all of these don't require thought, but some more so than others. Okay, so first of all, the stuff at the bottom, the asymptotes, just cross those out for now. These don't have any asymptotes. We're not going to deal with that. So we're not even going to talk about asymptotes. All right, but we are going to talk about the rest of this stuff. Yeah, they don't stack. Sorry. Just set it next to it on the floor. Yeah, thank you. Okay, so minimum, maximum values. Okay. The absolute value graph continues to go down or up, so it can only have one. It can't have a minimum and a maximum. It has one or the other. So in your parent function, does the graph have a minimum or a maximum? A minimum. The parent function faces upward, right? Oh, yeah, no. Parent function faces upward, which means you can only clearly define a minimum point. So for maximum value, there's none. For minimum value, it's 0. This is the y value. It's not a point because it specifically is asking for a value. So be aware, because you will get docked like half points if you're not interpreting the meaning correctly. So this is just meaning like what's the lowest y value that you reach, and that's 0. Okay? What would the axis of symmetry be? Yes. Yeah, it goes through the vertex. And it's a vertical line, right? That's where it would fold in half. And vertical lines are x equals. So this is x equals 0. This should always match the x coordinate of your vertex. Otherwise, it would be to the left or to the right. And when you folded it, it wouldn't work out symmetrical. Okay? The rate of change is just the slope. So in the parent, the slope is 1, positive or negative. Okay? And then, do you guys know what 1 to 1 is? Okay, so do we know what being a function is? What is being a function? Yes. Okay, so close. Okay, he said no two x or y coordinates are the same, and it really means for every x that I pick, there will only be one y. But there could be another x that gives the same y, like y's could be the same. What kind of test do you run on a graph to check that? Yeah, so when you're putting vertical lines, you're basically just checking that entire x value, right? And seeing if more than one point would mean more than one y value came with that x value. Okay, so is the absolute value graph a function? Yes. Okay, to be 1 to 1, it has to follow that rule and like the inverse of that rule kind of idea. So for every x, there's only one y. And now we want to say like for every y, there's only one x. Okay? So think about points here. let's say that they are, well, this is the parent function, so 3, 3 and negative 3, 3. Okay? They pass the function rule because different x's can give the same y. That's fine. Okay? But do they pass the inverse of that rule? For every y, there's only one x. So when y is 3, x is 3. But over here, when y is 3, x is negative 3. Broke the rule, right? Can you think of a test we could run on the graph that would test this rule? Yeah, horizontal line test, because now we want to check a y value. So we want to go across the graph at that value and see if x violates it and hits it more than once, okay? So this graph is a function, and it passes the vertical line test, which kind of tests that. However, it does not pass the horizontal line test, which means it doesn't make the statement true that for every y there's only one x. To be one-to-one, you have to have both of those things. So this is not one-to-one, because though it's a function, it doesn't pass the inverse of that rule. Is that okay with everybody? Right? All right. So let's talk about the same things over here. This graph that faced downward would have no minimum value, but the maximum value would be at 6. Is that okay with everybody? Because our vertex reached a maximum of 6 as its y value. What would the axis of symmetry be in this graph? X equals 2. You guys okay with that? That line would go right through the vertex, a vertical line through the vertex. The rate of change on this one, the slope is 2/3. And is it one-to-one? Will any absolute value graph be one-to-one? No, because they're all v's, so they'll all violate that second part of the rule that we're trying to make true, okay? All right, so last thing we want to talk about is this increasing, decreasing interval, okay? So I'm actually going to open up another slide for this maybe. Yep. Maybe it's okay, so increasing, decreasing, you guys are looking in your parent function at a graph that looks like this, right? Okay. We are going to read the graph from left to right. Okay? If you're walking along the graph or reading the graph from left to right, when is it behaving where the y values are going down versus going up? Okay? So if I was sitting on this graph, left to right, right? At first I'm on this part, and as I move across the graph, I would be going down with my y values, which means this branch of the graph is decreasing. Is that okay with everybody? Then if I kept going, once I hit this vertex point and I move across this way, I would be following this branch of the graph where the y values happen to be increasing. However, in your second graph, looks like this, right? So if I'm reading the graph from left to right along the first branch of this graph, I am increasing, then I hit the vertex, and then I'm decreasing, okay? So over here, this part is considered increasing, and the next part is considered decreasing. So this is half the battle. So do we feel like we understand this half? Like we can look at a graph and say oh, you're increasing, you're decreasing, you're not doing either. You're increasing, you're decreasing. You can do it for all different kinds of shapes, okay? It's all as you read it like a book from left to right, how you identify those. But now we have to know how to write them properly. So we've identified them, and are we all okay with this is not decreasing because this arrow goes down. It's because left to right that has a negative sloping thing happen, because this arrow goes down too, but this branch is increasing because from left to right we would be climbing up it. Is that okay with everyone? All right, now how we write it. We write it in interval form. See on your paper that they're called intervals, increasing interval, decreasing interval, okay? But here's the thing. You don't actually write about any of the increase or decrease. You write about the domain on which it is increasing and the domain on which it is decreasing. So when I say we're going to write domain, what kind of values from the graph am I talking about? X values. So though my eyes had to see what was happening with Y to understand which part is decreasing and which part is increasing, my pencil needs to now go write about the X values at which that occurs. Okay? So in this graph here, your vertex, the point where you change position, is at 0, 0. We are focusing on the X values. So one of my intervals is all of these X's over here until 0. And then the other interval is all of the X's on this side of 0. Does that make sense? I'm thinking all about X's. Okay? So when I go to write my decreasing interval for this, it goes from what X value to which X value. And remember, when we're writing intervals, we write the smallest thing where this happens is this until the largest thing where this happens is this. So this graph is called decreasing. What's the smallest X value for which the graph is decreasing? Negative infinity. There is no place where it just stops and we say it's not going anymore, right? What is the largest value at which you could still consider the graph decreasing? 0. So our interval is from negative infinity to 0. I'm going to write it like this. They're not picky. I talked to the calc teacher. With increasing and decreasing intervals, you could use a bracket or a parenthesis here. There's like mixed opinions on whether that point is part of the increasing, decreasing, or not. So you can make that decision. We won't mark you wrong there. We will mark you wrong in domain and range because either that point is included or not. But with increasing, decreasing, kind of weird. Like, what is 0? I don't know. It's a point where I get to rest for a second. I don't know. Not be increasing or decreasing. Okay. So on your second graph over here, I'm going to just focus on decreasing intervals first. This vertex was at 2, 6, right? So one of my intervals is every X value that's below 2 and up until 2, the graph is behaving one way. Then at 2, you have that point where, like, what are you doing? Nobody knows, resting, something, which part of interval. And then it switches to a different behavior for every X value after 2. So over here, the decreasing interval is here, okay? I want to write the parts of the domain that corresponds to. What would we write down as our decreasing interval for that second graph? Yeah. Good. 2, infinity. So the decreasing interval here is from 2 until infinity because those are the X's where the graph is behaving like a decreasing thing. Okay? So you're listing the X values where the graph has this certain kind of behavior. Okay? All right, so let's do our increasing intervals. So over here, who thinks they can name the increasing interval in the parent function? Yes, sir. Good. Okay. From a 0 value of X, behaving in a way that we call increasing. Okay. What about our increasing interval over here in the second one that we graphed? Who can give us that? Yeah. Good. Okay. So from X values from negative infinity to 2, this graph is behaving in an increasing way. So you guys understand kind of the two parts to it. Your eyes have to look at what's happening with the graph from left to right with the Y values to understand which part is increasing or decreasing. But when you write it down, you don't write anything about the Y values. We want to really bad because we want to say, like, this goes from negative infinity to 6. Like, that's what we want to say. But that's not, they want to know what's happening with the domain. Okay, tell me the X's where the graph has this behavior. That's what they're asking you for. Is that okay with everybody? All right, so all your homework involves graphing or writing equations, so this should be enough to get you through that. Okay? Yes? Yes. So max and minimum values are Y values. If they say, so it's really tricky, and we learned this from the pre-calc teachers that we need to emphasize this for you. If they say like a maximum or minimum and don't say any other words after that, you would list a point. So like in this graph, because it faces upward, this is the lowest thing that we hit. This is a minimum point, right? And if they just the minimum, I could say 0, 0. And in this graph, I would say the same thing, but I would label this as a maximum. Okay, so this graph has no minimum and only a maximum. This graph has a minimum, but no maximum. Because they put the word value after it, they're talking about range, y values, and they just want to know what is the lowest value that the graph reaches or the highest value that the graph reaches as far as y. So this one, because it has no maximum, there's no highest value. But because it hits this minimum point, the minimum value is 0. And this one, no minimum, but because it hits this maximum point, the maximum value is 6. Does that clarify? Okay. Mm-hmm. Any other questions that you guys have? No? All right, so we're going to put this away. We're going to take our quiz on piecewise. You have as much time as we have left in the period. If you don't finish, you're not going to cry or anything because you're just going to get it back on Monday and we're going to go through it, okay? And so